All right, so the topic of our final lecture is about life deep in the earth. And so we talked last week about life in the clouds, and as we've usually gone during this semester, we'll do the opposite now and talk about how low can life be. And the two organisms we're going to talk about are a sulfate-reducing gram-positive bacterium, Desulfurutus, and a bacteriovorous nematode, Halicephalobus. And so let me start out by talking about what we're not going to talk about, because there are deep places that are very interesting subjects of their own, but aren't what we're going to talk about today. And so the really obvious one is the deep sea. There are lots of places in the sea where troughs and trenches, spreading centers, etc., make the sea really a very deep place. The Marianas Trench being the deepest of them. And the deep sea, although it's nowhere near as well inhabited as the shallow seas and coral reefs and rainforests and so forth, nevertheless, there's a fair bit of life in these deep sea areas. The sediment itself is full of bacteria and archaea, small animals and so forth, various kinds of eukaryotes. And then there are larger creatures that wander around. The chimera or ratfish is one that you see a lot. Some of the largest sharks in the world swim around in these deep seas, like the Greenland shark. This picture here is a whale fall, that is a place where a whale has died and sunk to the bottom, and it creates kind of an oasis on the sea floor, much the same way that a hydrothermal vent does. The deep seas are cold. They are nutrient poor and they have high pressure. Normally when you think about the things that might be hard to live in the deep sea, you think of high pressure. It turns out though that, unless you've got gas spaces like your lungs or whatever, pressure of this sort doesn't really matter because water is incompressible, and so when you go deep down in the water, although there's a lot of pressure pushing in on you, your body pushes right back with exactly the same amount of pressure, and so that's not really an issue. You don't even notice it. There are a few things in your body that have to be adapted to live at really high pressures. This has to do a lot with membrane lipids and things like nerve synapses, but they seem to be pretty easy adaptations, and organisms have no trouble with those. We're also not going to talk about caves. There's some really cool microbiology about caves, but we're not going to talk about that today. There's a lot of biology in caves, particularly very near the entrance where creatures are coming and going or where nutrients are washing in on a steady basis. Deep in cave systems, nutrients tend to be extremely limiting. If the nutrients have to come in by percolation from the water above or around them, that water has percolated through what amounts to an enormous filtration system before it ever makes its way into the cave. And so organisms that live deep, deep, deep in the caves typically are excruciatingly limited for nutrients. But again, we're not going to talk about those. We're also not going to talk about soil. And so if you look at the surface of our planet, most of biology happens within a few meters of the interface between the air and water above and the soil or sediment below. And so this is a cross section of a grassland, and a couple of meters above the ground there's nothing there but air. A couple of meters below it and the dirt has turned into basically broken up rock and sand and silt. All the action is right there at the interface. And this is a common feature of ecology, is that most of biology happens at interfaces between different things. We're not going to talk about soil. There's a great soil microclass here at NC State, and particularly if you become a microbiology major, which you should, you might consider taking the soil microclass. But instead, we're going to talk about organisms that live much deeper than this, deep, deep down in the bedrock. And so here's a generalized cross-section of the eastern coast of the United States where we are. And you can see the Piedmont and coastal plain, the Blue Ridge, etc. Much of the surface of this is sedimentary rock, particularly near the ocean, and it's more transformed metamorphic rock deeper down. And you can see that this the shape and features of this crust are really the result of their long geologic history. And for someone who knows a lot about geology, which I am not, it's pretty straightforward to recreate the history of our area just by looking back at the geology and where these different rock layers are and how old they are and where they come from and all that sort of thing. Now, life needs water. And so you might wonder, well, if you're down in the rock, where do organisms get water? Well, it turns out there's a lot of water underground. And so this is an image of the aquifers. It's kind of a generic aquifer of the East Coast. And you can see the coastal plain there is full of aquifers. And some of them are shallow aquifers. These are places where the water charges in during rains and typical groundwater. And the cycling time for these is fairly short. That is, the water goes in and then it comes out somewhere or is pulled out or flows into the sea pretty quickly. The deeper you go, the aquifers get older and older, meaning that the water percolates in at a charging center somewhere on the left, soaks into the aquifer, and it's there for thousands of years before it makes its way to the sea. And on the right, you can see what they call the saltwater interface. This is basically the groundwater of the ocean, and the two push at each other. And so the groundwater from the sea, from the ground, pushes up underneath the ocean. But our attempts to use this coastal water by drawing the water out of wells depletes waters in the aquifers, and as a result, that saltwater interface moves inland, and this is a big problem for water use in North Carolina. Now, don't get me wrong, these aquifers aren't like giant oceans under the water. These aquifers are places where the rock is cracked or broken, and it's the water that fills the void spaces in these cracks or the pores in porous rock. It's the water. Most of an aquifer is still rock, of course, by a large bit. And you can kind of see that here. And so this is a road cut, of course, and you can see kind of the geologic history pulled through here. This is a dike, and so there's several layers of sedimentary rock, and then pushed up through that is a vertical band of metamorphic rock. This is where granite comes from, and so this rock was fluid and pushed its way up through there and then solidified, very highly transformed, of course. But all this twisting and turning and bending of the layers of rock cracks the rock and breaks it up, and oftentimes separates layers, and the layers slide across each other. And so these voids between layers in the pores of the rock itself and in the cracks and gravelized stuff that's inside there, that fills up with water. And it's the organisms that live in these voids that we're talking about. Of course, the deeper you go in the rock, the greater the weight of the ground above it, which pushes down on those rocks and compresses them. Now, the rock itself isn't very compressible, but certainly the voids are. And so the weight above packs that rock down tighter and tighter and tighter the deeper you go. And so the voids get smaller and become less and less of a fraction of the rock as you go down. Water gets scarcer the deeper you go down. So what limits what kind of life or how much life can live deep in the ground? Well, number one always, of course, is how much water there is. There needs to be water there in order for there to be living thing. Another thing, of course, is rock porosity. That is, and that's related to water. That is, how much void space is there in the rock that can be filled up with water? You know, in something like a sandstone, there might be quite a bit of void, or if it's gravelized rock, then there might be a lot of space in between. But if it's highly compressed, there may not be very much. Temperature is another one. The deeper you go in the crust, the higher the temperature is overall. And so obviously if you go very, very deep, the temperature is going to be too high for any living things to exist. The chemical composition of the water. You might imagine that even if there's water in a rock, if it's a toxic rock, or if it creates a highly acidic or highly alkaline water, then that may limit what kinds of organisms, or if organisms, can live in that environment. Once again, there's pressure, but again, that turns out not to be too much of an issue. One of the big ones is nutrient limitation. That water had to get there. And generally speaking, that means percolating through miles and miles, because it doesn't generally go straight down, of what amount to a sand filter, filtering out all the particles, and organisms in these other places, closer to the surface, get the nutrients. But what percolates down into the deep environment is not very much. So let's talk about one of these organisms, Desulfurutus Doxyvator. I'm not sure I'm pronouncing that correctly. Now this organism is not the bacterium that's been found deepest in the crust, but it's interesting for other reasons. It is deep in the crust. It's interesting for reasons that are unrelated to how deep it is. This organism was isolated in 2009, almost 3 kilometers deep in an African gold mine. Gold, of course, is very precious, and so, and like diamonds then, people were willing to dig very, very deep mines to collect whatever they can. The rock temperature at this depth is 60 degrees centigrade. Excuse me. And the pH of the groundwater in these rocks is 9.3. The water, of course, there's no oxygen in the water at this depth, and so any organism living there is anaerobic, alkalophilic, and thermophilic. The groundwater here has no measurable nutritional value. It has no carbon in it, as far as anyone can tell. And there's only one detectable organism in this environment. That's Desulfurutus. No other organisms seem to live in this place, and so it's living on its own. This organism is a gram-positive organism. It's generally related to Clostridia, and like Clostridia, it forms endospores when its ability to grow is compromised. It's a sulfate-reducing chemoautotroph. What does that mean? That means that it's reducing sulfate to sulfide in order to generate energy. It does not generate energy using any organic chemistry. So that means it's chemotrophic. It is autotrophic, meaning that it fixes its own carbon. It doesn't need organic carbon for growth either. It makes its own. It is an obligate anaerobe. It cannot tolerate the presence of oxygen. Well, this is a tough organism to grow, and it's hard to do a lot with, and so the first thing that the folks did was to sequence its genome to figure out what genes it has, what enzymes it can make, to see if they could see how it makes a living. This is particularly interesting because this organism does live in complete isolation, and the genome reveals that it is a complete prototroph, meaning that it can make everything it needs itself. It can make all 20 amino acids, it can make all purines and pyrimidines, it can make all of the cofactors it needs. In other words, it doesn't have any essential amino acids, it makes its own amino acids, and it doesn't have any vitamin requirements. It can make all of its vitamins or cofactors itself. It does have the genes for import proteins for bringing in things like glucose if those become available. But in general, it seems to make its living entirely through inorganics. Interestingly, so how does it make a living? How does it do sulfate reduction, which is how it makes a living in this environment? The way it does this, it seems, is through the radioactive decay of uranium, which is not abundant, but it's present in this environment. The radioactive decay of uranium emits radioactive particles, and these do some really interesting things. One of them is those radioactive particles fly through the water, they hydrolyze water and generate carbonate, hydrogen peroxide, and carbon monoxide. And so although there's no nutrition in the water itself, there's the energy of this radioactive decay generates both oxidized and reduced compounds that can be put back together again and yield energy. And so the passage of the radioactive decay particles through calcium carbonate or other carbonate rocks generates carbonate, which is basically dissolved CO2. It can also generate some ammonium from ammonium-bearing rocks. When it goes through the water, it hydrolyzes the water to make oxidative reactive oxygen intermediates, which ultimately end up as hydrogen peroxide. And this hydrogen peroxide reacts with pyrite in the rock to generate sulfate. The other part of pyrite, of course, is iron. That iron that's released then can react with phosphate-bearing rock to release phosphate into the water, which of course organisms also need. And so by generating both sulfate and hydrogen, this radioactive decay provides an energy source for the organisms that live in the surrounding groundwater. And this organism then takes up that sulfate and using hydrogenases reduces it back down to hydrogen sulfide, which then can serve as the substrate for further reoxidation from this radioactive decay. In other words, this organism is powered by radioactive decay, and it is the only organism known that is not powered directly or indirectly by sunlight. All the rest of life on Earth is powered by the sun. Even organisms in deep-sea hydrothermal vents. There was a time when people said that these organisms live in an ecosystem separate from the sun, but that's not true because that geologic fluid that flows out of the vents can only provide energy to the organisms around it because it mixes with the deep ocean water, which is rich in oxygen, which is the product of photosynthesis. And so this organism is different. This organism is entirely powered by the radioactive decay of uranium, although of course not directly. Hydrogen is the electron donor, generated by pyrolysis of water, and sulfate generated by the reaction of hydrogen peroxide, which is generated by the pyrolysis of water, and sulfate that just reacts with that. This organism can even fix its own nitrogen, so nitrogen gas dissolved in the water can be fixed into organic nitrogen. This organism needs water, it needs CO2, carbonate or bicarbonate dissolved in water, hydrogen, sulfate, phosphate, nitrogen gas or ammonium, and some trace minerals, and that's it. It doesn't need any organic carbon in any form at all. That's a pretty amazing creature. That's doing a lot more chemistry and a lot more interesting stuff, to tell you the truth, than humans can do. All right, let's talk about another deep organism, um, Halicephalobus mephisto. This is the deepest living animal known. This is a nematode, a roundworm. They're small, they're not microscopic, but they're nearly microscopic. Um, they were found in 2011, once again in an African gold mine. It's found in a variety of mines up to 3.6 kilometers deep. That's just over 2 miles deep. This organism feeds on bacteria. It's related to other nematodes that are detritivores. They eat just bits of what people call detritus or amorphous, just organic gunk. This organism feeds specifically on bacteria. Interestingly, it reproduces asexually. They're not males and females or males and hermaphrodites as there are in other nematodes. They are all female. It's thermotolerant, as you might imagine, and it can live at very low oxygen concentrations, about 1% of atmospheric oxygen concentration. At 2 miles deep, it lives in an aquifer where the water's been underground for 3 to 12,000 years. And so you can surely imagine that this water doesn't have very much nutrition in it. They're feeding on bacteria, but they obviously aren't feeding on very many bacteria. It's probable that these organisms descended from these other nematodes that were washed deeper and deeper into these aquifers. All right, your task, as usual, go to the discussion page on the course Moodle site, start a discussion thread about something that you find interesting or something that lives deep in the sea or crust or in caves. Make it substantial, and it's due tonight at midnight. Wednesday for those of you in the Wednesday section, Thursday for those of you in the Thursday section. And then come back afterwards, no later than midnight Sunday night, and make a couple of comments on other people's threads. Make them substantial, make them meaningful. You guys have been doing a good job. Don't let off the gas until you cross the finish line. All this is due midnight Sunday night. Lastly, as a reminder, there is no final exam on this class. Once you've done with your discussion threads and secondary comments, you're done with this class. You guys have done a fantastic job. I'm really happy with how you guys did this semester, and I hope that all of you consider microbiology as a major. I've kind of made fun of this in the past during this semester, that I think you should all be micro majors. That's obviously not really true. You need to want to be a microbiology major in the same way that you need to want to be whatever major you decide to be. But please consider microbiology and amongst the other things that you might consider. And if you decide to become a micro major, or if you're considering it, please feel free to contact me and we can chat. Although John Olson is the director of the program, and you should probably talk with him. Once again, it's been a great semester. Thank you for being such good students, and hopefully I'll see you around in the future. Take care now.